Welcome to This Explainer. Today, we're diving straight into the complex, rapidly evolving, and frankly absolutely critical world of distributed energy grid cybersecurity. You know, as our power grids get more and more decentralized, packed with solar panels, battery storage, smart energy management systems, securing the whole shebang has literally never been more important. Our everyday lives rely entirely on continuous power. But how do we actually secure a decentralized grid? Well, that is where things get truly fascinating.
Okay, let's dive into this. There's a quote that perfectly captures a massive cyber paradox in modern infrastructure. Defensive efficiency is also offensive efficiency. We tend to think that taking a single, highly certified security standard and just slapping it onto millions of devices makes us safer. And sure, it makes things way more efficient for the defenders. But here's the catch. Making large systems uniformly safe actually standardizes the attack surface for hackers. Which brings us to our first major theme. Section 1. The illusion of certification. Now, to be totally clear, certification programs like Japan's JC Star labeling system are excellent. They are an absolutely necessary starting point for IoT security. They get rid of default passwords, they verify basic encryption, they force manufacturers to actually take responsibility for their supply chain. Yes, and a shiny sticker on a cardboard box absolutely does not guarantee a safe, dynamic grid over a 20-year operational lifespan.
So the crucial point here is that checking a compliance box can inadvertently create what we call security theater. It gives this false sense of security that actually blinds grid operators to the real, dynamic risks out there. Over decades of operation, equipment breaks and gets swapped out, routers get upgraded, cloud APIs change. A system that was fully certified and safe on day 1 might be running in a completely uncertified, totally different environment by day 1000.
Let's look at the real-world implications of this. Section 2. The systemic risk paradox.
Think about what happens when every single solar plant across a country uses the exact same certified setup. We create a homogenized attack surface. They all share the same firmware, the same over-the-air update mechanisms, the same APIs, the exact same cloud structures. So an attacker doesn't have to hack thousands of unique, quirky systems anymore. No way. They just write one automated exploit script. Because we gave them a standardized path, they have the potential to take down a massive, wide-area portion of the grid all at once. By standardizing our defense, we've essentially automated their attack.
So how do we fix this? Let's dismantle this static safety model. Section 3. 7 system design questions.
Now, what's really interesting here is how this shifts our entire perspective. Why do we focus all our energy on certifying a single point, like one specific solar inverter, instead of designing and securing the trust boundary? The trust boundary is that critical space between the wild, open internet and the closed, local network. If we protect the boundary itself, it honestly matters far less what happens to the individual points inside it.
And that's just the tip of the iceberg. We have to ask about dynamic drift. How can a static certification handle a network that's definitely going to change with new Wi-Fi over 20 years? And who is continuously proving the negative? Like, who verifies that only certified devices are plugged in? What happens when management breaks down or maintenance contracts change hands? Plus, why do we treat self-consumption solar the exact same as reverse flow solar? And finally, why do we completely ignore massive load-side asymmetry, like EV chargers that can trigger massive synchronous load shifts but heavily regulate solar panels?
The regulatory inconsistency is just glaring. For instance, solar photovoltaic architecture regulations prioritize certifying the internal equipment, the power conditioning systems and energy management systems, but wind power regulations, they prioritize the external boundaries, the gateways and firewalls. The whole trust boundary approach is already recognized and prioritized in wind power, so it really begs the question, why is solar being treated so differently?
And hey, this isn't just some academic debate. There is a ticking clock here. The Grid Code Study Group's implementation schedule slates mandatory cybersecurity measures for high-voltage solar for April 2027. That's literally right around the corner. It is absolutely crucial that we get this architecture correct right now, before these homogenized compliance frameworks lead to a mass deployment of highly vulnerable systems.
Let's move on and see how this builds into an actual solution. Section 4. Physics over software, and the introduction to LEAA.
LEA, it stands for Load Equivalent Autonomous Architecture. In plain English, it's a paradigm shift. It's a framework that elevates security away from static software compliance and relies instead on absolute, unbreakable physics-based resilience. Now, it doesn't replace certification, but it fills in those massive, dangerous gaps that software certification leaves behind.
So LEAA is built on 3 core pillars.
First, a physical air gap between the logic layer and the protection layer. Second, establishing load equivalence from the grid's perspective. And third, autonomous degradation, basically ensuring the system fails safely and actually stays operational rather than just totally shutting down during a crisis. Let's break those down.
The first pillar is the ultimate trump card: physics versus code. Human-written code in APIs, clouds, software updates, it will always have vulnerabilities. It just will. But physical laws do not. Under LEA, a reverse power flow prevention relay, an RPR, is hardwired to physically block power backflow. So even if the cloud or the energy management system is 100% compromised by hackers, that hardware relay operates independently based on electrical physics. You can't hack gravity, and you definitely can't hack a physical relay.
Which takes us right into daily operations. Section 5, Fail Operational Architecture.
And this brilliantly illustrates the second pillar, load equivalence. Think about it. If a self-consumption solar array is physically blocked from pushing power backward into the main grid, then from the grid's perspective, it's effectively just a heavy electrical load. It's literally equivalent to a large commercial air conditioner. By physically ensuring it cannot act as a supply-side threat, you completely neutralize the cyber risk model that justifies these massive software regulations in the first place.
The final pillar here is graceful degradation. Right now, a lot of IT-centric systems are designed to do an all-stop. They basically self-destruct and shut down entirely if they lose their internet connection. That is terrible for resilience. ELIA, on the other hand, allows facilities to survive locally. If the cloud drops, local solar generation just keeps right on going, using local measurements. If the main grid fails entirely, it safely disconnects and drops into an islanded business continuity plan mode, keeping your critical local systems powered up.
Let's wrap this up by looking forward. Section 6, 5 questions for policymakers.
Policymakers and grid operators really need to interrogate their own frameworks. Are we regulating the target or the boundary? Why in the world are wind and solar priorities treated differently? How do you properly evaluate post-operation equipment replacements when a system naturally drifts over time? And should a self-consumption system that physically cannot backflow into the grid share the exact same risk model as one that does? We've got to look way beyond checking compliance boxes and interrogate how we realistically manage 20-year energy assets.
Ultimately, the whole thing comes down to this core question. Does the policy aim for mere product certification or true system-wide resilience? A label on a box is a great start, but it is not a finish line. Are we building a grid just to pass a test, or are we architecting a grid designed to physically survive a crisis? I hope this explainer gives you the tools to ask these tough questions in your own engineering and policy circles. Thanks so much for tuning in, and keep pushing for true resilience.